Number 85. So we've got these aircraft engines and we're going to test them for an hour of flight and hopefully that they make it. Well, the probability is pretty high that they're going to make it for 1 hour, 0.999. And they're going to take 350 of these engines and do this 1 hour test and see how many of them make it. Well, first question is, explain why x is a binomial random variable. Well, we better check our bins. Is it binary? Yes, they either make it for an hour or they don't make it for an hour. Are they independent? Well, each engine test doesn't affect any other engine test. And how about the number? Well, that was set beforehand, so we got that. And the success rate, well, they tell us ahead of time is 0.99. So bins is okay. You would have to write that up if you're answering this question on a test. Letter B. Well, find the mean and standard deviation of x. So the mean would be, well, it's 350 times 0.999. It's the sample size times the probability. So we get 349.65. 349.65. So that's what we should expect to have happen. Okay? If we did this test over and over and over again, that's the average that we would get. So maybe one engine is going to fail. Maybe. Maybe two, maybe three. Well, that has to do with the standard deviation. Let's figure that out. The standard deviation is going to be, well, it's the number, 350, right, times the probability, and 1 minus the probability. Remember, those have to add up to 1, so that's going to be 0.001, and then take the square root of that whole thing. And it is 0.591. Okay, so basically, give or take half an engine, so maybe we'll have one engine fail on average. Maybe two, but that would be kind of surprising, I think. Actually, let's look at letter C. 2 engines failed. Oh my gosh. I was not expecting that. You're convinced the model engine is less reliable than it's supposed to be. What is the probability that you get x is less than or equal to 48? So, on this one, we would have to calculate what's the probability that no engines fail, or one engine fails, or 2 engines fail, right? So, x is less than or equal to 348 successes. Well, we would do by the binomial formula for this one and this one and this one and add them together. Or we would do, binomial CDF. Binomial CDF in the calculator. So I'm going to do that right now. Here we go. Second vars all the way down to binomial CDF. Let's see, the trials is 350, the probability is 0.999, and the value is 348, right? Because that's what it tells us. That equal to or less than that number, that's what binomial CDF does. And put that bad boy in there. Aha! 0.0485. 0.0485. So, what does that tell us? Well, we have about a 4% chance that we would have 2 or less engines fail. So, pretty low probability that that would actually happen. So that does make me a little bit suspicious of this test. All right, but that's for next chapter. Let's do the next one. Number 89, no replacement. So Clyde was talking about this, where if we keep taking things out of the population, it changes the probability of what's left in the population. That's that 10% rule. It messes with that success rate. I don't know if this is a great example, but I'm going to put it in here anyway. Let's just say that you're going to flip over 20 cards and see how many aces you get in those 20 cards. What's the probability of that happening? Well, when you flip over the first card, right, say it's this 6 of diamonds, you had a 1 out of 52 chance that that was going to be an ace of spades. Your second card, say 9 of spades, well, that changed a little bit. You had a 1 out of 51 chance that it was an ace of spades. The difference between these two is not that bad, but say you get to the 20th card, right? Well, the 20th card is, now you're a 1 out of 32 because there's only 32 cards left. That probability versus that probability becomes a problem. Okay, so that's why we want to have our population size 10% or less, or our sample size, sample size is 10% or less than what the population size is. And it has to do with messing around with the probability of success starts to change. Okay, that's number 89. Benford's law states that when you submit an account report to your company to get reimbursed, the number that you put for the amount of money that you are owed starts with a 1 or a 2 47.7% of the time. So in other words, you might put in an account for $112 or $218 or $29 or $19, but it always starts with a 1 or a 2 almost half of the time. So let's just say that we take a simple random sample from a population of 90 invoices and from the vendor and find that 29 have the first digit of 1 or 2. Do you suspect the invoice amounts are not genuine? Okay, let's figure this out. Well, if you had 90, right, how many would you expect to have a 1 or a 2? Well, let's figure that out. So the mean is, remember, it's the sample size times the probability, like that. So what is that number? Now we should expect to have about 42.93, but the number that we got was, what was it? It was 29. It seems a bit off. Well, what's the probability that that would happen? Well, let's do the standard deviation. So the standard deviation is going to be 90 times 0.477, 1 minus 0.477, 0.523, and then take the square root of that whole thing. So let me do that and see what it is. And that number is 4.74 approximately. 4.74 is our standard deviation. This is our expected value, or our average. Well, let's do a z-score. Now let's see, we got 29, right? That's the number we're interested in. We expected 42.93, standard deviation of 4.74. Okay, let's just do that to separate the stuff. Okay, let's find out what that number is. And that is negative 2.93. So if we drew a picture of this, right, it looks like this. Whoops. Looks like this. This tells us how many standard deviations we are below the middle. We start at 1. Wow, it's way down there, okay? So the fact that it is 29 or less, like that, right? So, what do we get? Oh, normal CDF. So we're way down here. 2.93, and I got for normal CDF 0.0016. So there's like a 0.16% chance that that would actually happen. Seems suspicious.